empty spaces. Second, he helped in the discovery of new elements. And the third was his classification helped in correcting the mass, the atomic mass of beryllium. Okay, so this was the discussion that I had. So let's talk about each thing. And yesterday I was talking about the correcting the atomic mass of beryllium. So which was anticipated or which was wrongly noted as beryllium's atomic mass as 3 into 4.5, which is somewhere around 13. But later on, this is anticipated one and which is wrong. And the corrected one is this, which is 9. So 9 is the atomic mass of beryllium. Okay. So this was about yesterday's discussion, and now let's continue. Empty spaces. What exactly empty spaces he left, and how did it really help the other scientists to discover the new elements? Okay. So for that, this is what it is. So Eka aluminium and the discovered. See, this was the properties that Mendeleev has expected to be, and later on, after several years, the elements were discovered and the properties were matching with what he expected to be. So the first one, that is atomic mass. He said aluminium mass, boron, aluminium, gallium, indium. So these are the elements. So if boron, he left an empty space here. Today we find gallium, today we find germanium, but at regular intervals he left empty spaces because the atomic mass is not matching. So what he said is, he left empty spaces and he said aluminium is having so and so nature, gallium also will have a similar nature of aluminium, similar nature. So that's why he has quoted the name Eka aluminium or similar to aluminium. So mass is 68, he anticipated 68. Later on, the element when discovered was found to be 70, so correct. And mass of Eka silicon was 72. Later on, the discovered element is 72.6. And as same way, density, as I already said, in terms of how do we calculate the densities when we know the solid state of that, right? So 5.9, 5.94, exactly same almost. And Eka silicon 5.5, discovered element was 5.36, almost same. And melting point, he said, he did not give the value, but he said that melting point should be less or low because aluminum can be easily melted. So Eka aluminum should also be easily melted. So he anticipated to be low, and discovered element is found to be as 30.2, and true, correct. And Eka silicon, which was very high, he said it should be very high, and it is very much true that it is 1231, okay, Kelvin. So this amount of huge temperature is required for the melting of it. And similarly, oxides. We know that aluminum oxide formula Al2O3. In case someone, see the very important ones, if you are not knowing the formulas of the compounds, then it's really tough. I always tell to my students, like 5 basic things are very important to learn chemistry. Number 1, the periodic table, that is first 30 elements. Number 2, the atomic masses of 30 elements. Number 3, you must know the valencies of the 30 elements. Only when you know the valencies, you can write the formula of a compound. Only when you know the formula, you can write the reaction. Okay, so these are the 5 steps. So you must learn these 5 things to make your study of chemistry easy. Most students who face difficulty in chemistry is because they lack one of these. Alright, so hoping that you will be learning the charges and aluminum oxide. In fact, if you remember in your 9th or 10th classes, aluminum's charge is +3, oxygen is -2, then we crisscross and we write it as Al2O3, right? So to write the formula, you must know charges. Okay, so do remember this. Alright, so if aluminum oxide is forming Al2O3 type, then Eka aluminum also should form E2O3 type, which he anticipated. And later on, after the element was discovered, which is gallium. So boron, aluminum, gallium. So gallium will have the oxides of gallium is Ga2O3, same as aluminium, and silicon dioxide normally. Okay, so this should be or the discovered element GeO2, and hydrides same way. Hydrides, when you talk about hydrides, AlCl3 or AlBr3. So aluminium or Eka aluminum will be ECl3. Same way gallium chloride is formed and GeCl4 is formed. So this is the main advantage or the merits of metal is periodic table. Clear? Okay. So now let's talk about, that was the merits, and in fact he has got with demerits as well. Let's talk about the demerits now. First, the position of hydrogen. Position of, not first, let me write like this. The position of various elements. Position of number 1, hydrogen. It is unjustified like the position of hydrogen. Even till today we have this problem. That is, hydrogen, either it falls in the first group or should it fall in the 17th group. For example, hydrogen, if you have studied about hydrogen's configuration, what is the hydrogen's configuration? It is 1s1. So now, either it can gain one electron to become helium, gain one electron to become helium. Gaining one electron proves that its nature is like halogens. Okay, halogens' general tendency is to grab one electron and become noble gas. Same way, hydrogen is also behaving. Other side is this: hydrogen can use up this one electron and become as H plus, more electropositive element, which is the nature of first group elements, Li plus, Na plus, K plus. Okay, the nature of metals nature. So because of this two, see, even till today we have this like hydrogen, position of hydrogen is still like it could be on the that is 17th group, or it can also be on the first group. So the position of hydrogen is not justified. Second, the other demerits is he did not explain the position of lanthanides and actinides also. Position of lanthanides and actinides are also great job for him. And third one, the position of isotopes cannot be explained. What do you mean by isotopes? Remember isotopes, what is isotope? For example, in 9th or 10th I hope. So you have studied about isotopes and isobars. Isotope having, remember like this, difference in the top. Okay. Difference in the top. Just a mnemonic or way to memorize the words isotopes and isobars. For most of the students it is really confusing, so that's why I am making you to remember in this way. Okay, the other one is isobars. Fine. So this thing difference in the bar, B stands for bottom. Okay, B stands for bottom. What is this top and bottom? For any element to represent, we have the following terms, okay, which you must be very much familiar with. That is, an element will have a symbol and it is also having two positions. That is A and Z, where A stands for mass number where A stands for mass number and Z stands for atomic number. Mass number is nothing but number of protons. Atomic number is protons plus number of neutrons. Atomic number is number of protons, which is also equals to number of electrons. Okay, so just putting the demerits for some time aside, let's understand these points what I have written. An element has a symbol, and at the top we represent by a mass number, and at the bottom we represent an atomic number. Mass number speaks about number of protons plus number of neutrons. Atomic number speaks about number of protons, which is also equals to number of electrons. Some students write atomic number is defined as number of electrons. No, it is not correct all the time. What do you mean by all the time, sir? I mean, protons number is the perfect definition for atomic number. When you take the charged particles, charged species, the number of electrons definition will not stand correct. For example, if I want to say let's say I was talking about isotopes, right? So difference in the top, difference in the bottom. 6C12 and 6C14, for example. In fact, isotopes means same elements having different properties. So difference in the top, they are differing in the top. Same elements, 6, same atomic number but different mass number. So they are called as isotopes. Okay, same atomic number but different mass number, isotopes. Differing in the top, isotopes. Then isobars. For example, calcium and let me use argon and potassium. Calcium is also fine. 40, whose atomic mass is, and argon, and these two elements are differing from each other. Okay, so 1 second. Okay, so these are what? Isobars. Fine. So they have the same difference in the bottom. So their atomic mass, calcium's atomic number is different from argon. So if you find calcium is you have argon on 10, 20, sorry 18, and calcium is on 20. So 20 and 18. Okay. So they differ in the bottom, same in the top. Differ in the bottom, isobars. Very important area. One last time. Isotopes, isobars. Isotopes, they differ in the top. Isobars, they differ in the bottom. And what is that bottom? For an element you have A and Z. A stands for mass number, Z stands for atomic number. So by definition, what is isotope? Isotopes are those elements having same atomic number but different mass number. Okay, fine. So by this, what is that you wanted to prove here? Merits. See, isotopes, while we were talking about Mendeleev's, he said his classification is based on the atomic mass. So if the elements are having same atomic number but different mass, then they must be positioned differently. Their position 6C12 and 6C14 must be at different positions. But in the isotopes, he has placed the carbon, all the isotopes at one position only. Okay. So this thing, why he placed the carbon isotopes at one position only, cannot be justified. So that's the disadvantage of the demerit of Mendeleev's. Okay, fine. Moving ahead. So the next one is about position of lanthanides and actinides, isotopes, and similarly position of copper and position of mercury, and position of the potassium and argon. Okay, see, argon's mass is relatively higher than potassium, but when you talk about the position, he positioned it like this only. Argon comes first, then potassium comes next. So his classification did not explain. Argon is coming first and potassium is coming next. But when you talk about the mass, potassium's mass is lesser than argon's mass. So logically this should come next to potassium, but it is coming ahead. So this thing cannot be explained by the Bandeligs. And copper and mercury, even though they are having same properties, but they are positioned different. Okay, and there are also some other elements like alkali metals and coinage metals. Their position is also unexplained. They have the same different properties, but their positions are same. So these are the demerits, that is position of hydrogen, position of lanthanides and actinides, position of isotopes, position of copper and mercury, position of potassium and argon, position of alkali metals and coinage metals. All of the position elements is standing unjustified. Okay, so these are the demerits of Mendeleev's periodic table. Alright, so now let's continue our discussion, that is Mosley's periodic table, which is also termed as modern periodic table. Okay, so exactly the periodic table that we follow today is given by Mosley's, and his classification, see in fact how it has come up also. Be it Daubernier, be it Newlands, be it the other one, that is Ruthermeier and the Mendeleev's. All these scientists have considered the classification basing on the atomic mass. But Mosley's performing an experiment, okay, so he proves that the frequency of an there is an expression which explains about, see, we have a metal surface and a strong beam of light or a strong beam of electrons. When they are subjected towards this metal, there are some rays that is coming out. Okay, in fact they are called as X-rays. So Mosley is making a study on these X-rays that are coming out or that are ejecting out when a beam of electrons is hit on the metal surface. So when this hit, X-rays comes, and X-rays frequency, this is what? Frequency. The frequency of X-ray is proportional or is equals to A into Z minus B whole square. Okay, so this is the expression. In fact, regarding this expression, regarding this how the experiment and all, we will study in modern physics. As far as chemistry is concerned, he has proven a very different aspect. All the scientists were taking atomic mass as the criteria, but he has proved that Z, that is atomic number, is the criteria for classifying the periodic table. So which is a very, very important point. All of a sudden the entire notion has been changed to atomic number. So let's talk about that. So point is, Mosley's study on the frequency of the X-rays, that are coming out from a metal sheet, says that it is related with what? Atomic number. Z stands for atomic number. Alright. So let's give the law. He says that if the elements are arranged in the increasing order of atomic number, the elements with same properties falls in same group. In other words, he has grouped the elements in such a way that the elements are arranged in the increasing order of atomic number. Okay, and basing on that, today we have the modern periodic table as this. So the modern periodic table consists of the following things. We have the 7, in fact 1, 2, 3, 4, 5, 6, 7. So we have altogether 7 periods, and we have how many? 18 groups. Okay, the horizontal periods and vertical groups. Now in these 7 periods and 18 groups, let's see the elements, which period is containing how many number of elements. The first one, the first period, which is called as short period, this contains only So the periodic table is like this, where we see that there are 7 periods and 18 groups. And in this, the first period contains only 2 elements. 2, and second, you can see very clearly that the second period contains 8, third also 8, this one has 18, 18, this is a magic number, you can call it as 2, 8, 8, 18, 18 and 32, and this one is 19 and in fact incomplete. Okay, so these are the things that you must be knowing very importantly, that is the magic number 2, 8, 8, 18, 18, 32, 19, and in fact the last one, that is the 7th period, is still incomplete. That is why we say incomplete, because the elements have to be yet discovered. Okay, there are many more elements that have to be discovered in fact. So on a whole, the bottom line is this: 7 periods, 18 groups, first period 2, 8, 8, 18, 18, 32 and 19. Now in this, the periodic table is classified into groups as well, sorry, into blocks as well. The first 2 groups, okay, the first 2 groups, they are called as S block. This thing, they are called as what? S block elements. The first 2. These 2 are called as S block elements. And the last 6, they are called as P block elements. The last 6. Why first 2 and why last 6? Depending upon the number of orbitals. That is, S subshell will have only 1 orbital, and each orbital can have maximum 2 electrons. So those 1 electron is accepted or entering here will fall under first group, and if it is in the second, then you call it as the second electron, second group. Same way, we have 3 orbitals of P, Px, Py and Pz. Total number of electrons, that is twice of the number of orbitals, so 6. That's why we have 1, 2, 3, 4, 5, 6. So P block contains 6 groups. What should you expect for D? D has how many? 5 orbitals, right? So 5 orbitals into 2, 10. So there must be 10. In fact, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so this is what my D block elements are. And at the bottom, you can see these 2, that is La and Ac. Fine. So after lanthanum, we have the lanthanides. These are called as lanthanides and actinides. These are termed as the transition. In fact, these are called as transition. These 2, they are called as inner transition. Inner transition or F block elements. Okay, F block elements. How many elements should it be there in F block? We know that F block contains 7 orbitals, so there must be 7 to 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Oh, 15? No. This comes in the third, that is lanthanum and actinium. You can see these two, they both fall under the D block. Okay, lanthanum and actinium falls under what? Here. And these, they fall under F block. So, do not be confused. These fall under the F block. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, there's a mistake in this. So lanthanum and actinium falls under, do remember this, very commonly made mistake. Lanthanum and actinium belongs to D block, not F block. Okay, these are F block elements. Alright. Alright, so the important points that you must be knowing is which period is starting with what element, that is important, and which period is ending with what elements, that is also important. So all the periods starts with a metal. Okay, except the first period. The first period is hydrogen, which is a non-metal. Okay, and here also you must be knowing how many metals and how many non-metals and metalloids are there. The S block is purely of metals. The P block contains all the three: metals, all metalloids and all non-metals. Okay, so here you can see that P block elements: carbon, nitrogen, oxygen, phosphorus, sulfur, selenium. Okay, so these, they act as non-metals. Okay, and we also have the metalloids, that is aluminum, silicon, germanium, these things. You can see the step A here. So they are the metalloids, and it contains all non-metals, that is helium, they are all noble gases, they are non-metals. Okay, so the thing is, metals completely, S block will have only metals, P block will have non-metals, metalloids, as well as few metals. You can see tin, okay, thallium, lead is a metal. Okay, so here you can find the metals, and here you can find the metalloids, and these are all non-metals. Okay, and D block elements all are metals. Okay, so these are all metals. So every period starts with a metal and ends with a non-metal, and in that the first period is hydrogen, helium. The second period is lithium, ending with fluorine. Okay, apart from noble gases, I am talking about lithium and fluorine, sodium and chlorine, potassium and bromine, and rubidium and iodine, cesium and antimony, then francium, and we have, that is TS. Not much necessary because these are all radioactive elements and we will not study much about them. So this is what about S block, P block, D and F. Now let's talk about the position of the various elements, how to identify them. Okay, and before that, the general electronic configurations. You take any S block element. Alright, so now let's talk about the very important area for competitive exams. Very frequently asked is this. Yeah. So general electronic configuration. If an element is belonging to S block, its configuration is always general electronic configuration is NS1 and 122. And if it is a P block, NS2 NP126. D block N-1 D1210 NS022. And F block N-2 F1214 N-1 D N-1 D 021 NS2. Now what is this general electronic configuration? First of all, you need to understand the S block, P block, D block and F block elements. When is an element termed as an S block? Very simple. If the valence electron is entering into the S orbital of nth shell. One more time. S orbital of nth shell. For example, let me take, let's say I have lithium. Okay, so lithium's case, the last electron, we know that in the in the lithium's case, we have the first shell. The first shell comprises of one orbital, that is s orbital itself, and s orbital can accommodate 2 electrons maximum, 2 electrons. The second shell contains 2 subshells, which are s and p. Each subshell contains again orbitals. S will contain only one, so that is 2 electrons in its s orbital, and p will contain 3, that is px, py and pz. So in the px, 1 electron is getting filled. Okay, so I'm sorry, so this is lithium I'm talking about. So this p orbital, even though it is there, it is of no use because the electrons does not get filled in this. In the second shell we have only 1 electron, that is in s orbital of, this is what my s orbital of the second shell. So can I call this as s block element? Yes, the valence electron is entering into the s orbital. So that's why lithium should belong to the s block. So this is what I can say like s block element. If you talk about boron, okay, so boron also same thing. So if you talk about boron, so if you talk about boron has again the same. First shell is containing only 1, that is s orbital. Okay, you can see that it is having only s orbital, and in that s orbital we have 2 electrons filled. And in the second shell we have s as well as p. S contains 2 electrons. Now the third electron has to come into the next orbital, that is p. So because the newly coming electron is entering into the p, then we term it as what block element? P block element. Okay, same goes with G, same goes with F. But only thing is, in the general electronic confirmation, we have to remember in the P block NS1 to 2, NS2, NP6, that is okay. But if D block N-1, that is not ultimate shell, this is called as penultimate shell. Okay, so N-1D 1 to 10, NS0 to 2. And for F block N-2, F 1 to 14, 1-1D 0 to 1, NS2. So do remember this general electronic configurations very importantly. Okay, alright. So just we spoke about the configurations, and now let's talk about the elements S, P, D. Let's focus on D. In the D we have series. This is called as 3D series, 4D series, 5D, 6D. Okay, so we have 4 series, in fact 3D, 4D, 5D and 6D series. The 3D series starts with scandium, ends with zinc. Do you remember this? Scandium and zinc, yttrium and cadmium. Okay, and here we have lanthanide, as I said, lanthanium, La, lanthanium and actinium. These two fall under the D block only. From here falls our F block. Lanthanium and actinium falls under D block, and hafnium and mercury. Okay, so these are the starting of 3D, 4D, 5D, 6D series. Okay, and 5D and 6D start with lanthanum and actinium. And if you talk about F block, we have 2 series. Okay, so selenium and thorium. So these are the 2 series that you have to remember. Okay, so that's all about the periodic classification. Roughly recapitulating the things: S, P, D and F. S contains 2, P contains 6, D contains 10, F contains 14 elements, and all the one important point, all the F block elements falls under third group. Okay, don't forget, all the F block elements falls under third group only. In the next class we'll talk about how to identify the position of the elements if the atomic number is given. Okay, let's stop for here.